3.5, we're going to start looking at complex zeros of polynomial functions. So we're no longer restricting ourselves just to real roots or rational roots. Now we're allowing complex roots. So the root is where this is going to equal 0, where that graph crosses the x-axis. Now in a case like this, what you should do would be factor out the GCF, which is an x cubed. That's going to be behind x squared plus 9. So I have this times this equals 0. Okay, not so bad. Now when I multiply this times this and get 0, there's two possibilities. Either x cubed equals 0 or x squared plus 9 equals 0. Now x cubed equals 0, that's really a root of multiplicity 3. I hope you see that. It's really x times x times x equals 0. So you have x equals 0 as a root 3 times. So what kind of behavior do you expect when you look at the graph of this? What's it going to look like? Bounce, wiggle, or straight through? A wiggle. All right, so it's going to have a little wiggle as it goes through the origin. But how about here? Where does this equal 0? Well, x squared equals negative 9. X is going to be plus or minus, and please don't forget the plus or minus, the square root of negative 9. What's the square root of negative 9? 3i. So we got two complex roots. One at positive 3i and one at negative 3i. Okay. Now that makes sense because we've accounted for the roots at x equals 0. There's 3 of them. That means there's going to be 2 more that are kind of unaccounted for. And if we look at the graph, we see exactly that. We have a wiggle at x equals 0, but that's the only place that this graph crosses the x-axis. You can zoom out as much as you want. You're only going to find that it crosses the x-axis at that one place. So, okay, we've got all the roots. We've got them accounted for. Let's take a look at problem number 16. P of x equals x cubed minus 8. So again, if I'm looking for where the roots are, I need to solve where that's equal to 0. So how can we do that? Well, I guess the first way to start out with is a little bit of a reminder for you, and that is how to factor the difference of cubes. So let's see if we can't do that. The difference of cubes is always going to factor as a binomial times a trinomial. So the binomial comes from asking yourself, well, what do I cube to get each of these? So that would be an x here and a 2 here. Well, that's the binomial. Now my little trick for helping students remember how this factors is to use these two to help generate these 3. So we'll start with taking the first one times itself. X times x, that's an x squared. The second one times itself. 2 times 2 is a 4. But I need something different to get that middle term. I've multiplied this by itself. I've multiplied this by itself. What different can I do to get a third term? Multiply them together. So x times 2, we'll write it as 2x. Now there's one last thing that I need to fill in, and that's the signs here. Good. The signs follow this mnemonic. These two signs are the same. So that puts a minus there. The next two signs, this one and this one, are opposite. So that's a plus there, and the last one is always positive. So there's my factorization. And you can see one of the roots. Yes?
Did you get x minus 2 by using the cube root of x there?
Yes, exactly. You ask yourself, what do you cube to get each of these? So effectively, you're taking the cube root. So that's how you get that first binomial. Now you can read off one of the roots here, right? Where does this equal 0? X equal 2. All right. Lucas, let me put you to the test here. Can you factor this one?
X plus 2x plus...
Nope.
I'm sorry, they're always prime.
It's prime. Sorry. I set you up. Shame on me. All right. You can't factor that one. When you factor the difference of cubes, this second term here is always going to be prime. It's all right. Really, no, I feel bad. No, if I had a conscience, I'd feel guilty. All right, let's keep going. X squared plus 2x plus 4 equals 0. Well, we need to figure out where that is equal to 0. And if we can't factor it, what's our fallback? What can we always go to? Quadratic formula. So let's go to the quadratic formula. That's going to be negative 2 plus or minus the square root of 2 squared minus 4 times a times c. So a is 1, c is 4, over 2 times 1. So let's keep playing around with that. That's going to be negative 2 plus or minus the square root of 4 minus 16 over 2. And I'm not sure what kind of wishful thinking happens a lot of times when people do this. But what should you get underneath the radical? Negative 12. A lot of times that negative just disappears. It's like, no, I don't want to deal with complex numbers. It's there. When you're solving something like this, you're going to get that. We'll take a look back at that in a second. So let me split that up because I want and need to simplify that. I'm going to split it up into 3 radicals. Can anyone suggest what I'm going to put in each of these?
4, 3, and -1.
Good. 4, 3, and -1. Always factor out a -1 when you're working with a radical of a negative number. And then the 4, our choice of 4 is because 4 is a perfect square. And that goes into 12 evenly. And it leaves the 3. So what does that give me? Negative 2 plus or minus... Yeah, I'm going to leave the I out in front. And the reason for that is because sometimes when people put the I behind the radical, all of a sudden that I gets tucked under the radical. We will not take the square root of I in this class. Not that you can't, but it's probably best left to a trigonometry class before we do that. You can't cancel this 2 into that 2. You can't cancel this 2 into that 2. What I would suggest is that we factor out the 2. That's going to leave behind -1 plus or minus I times the square root of 3 over 2. And now we can have some cancellation fun. 2's cancel, and you're left with -1 plus or minus I times the square root of 3. I factored out the 2 here. So if you distribute, 2 times -1 is -2. But then
The 2 from after the plus minus sign.
I just factored out the 2. So I divided each of these by 2.
Oh, you took everything.
So yeah, I factored it out of everything. So we have those 2 possibilities for x, or x equal 2. Let's look at the graph. How many times should we see the graph cross the x-axis? Once. Should only cross at x equal 2. And let's see that that's true. So we'll use this one. Let's just rewrite that as x cubed minus 8. Beautiful. Look, it even did the y-intercept for me and the x-intercept. So -8 and 2 respectively. But nice. What you see here is kind of what we expected. It crosses the x-axis once. By the way, is this a bounce wiggler straight through here at x equal 2? Straight through. And that corresponds to a root of multiplicity 1. X equal 2 is just a root once. The other 2 roots are complex. So we don't see those cross the x-axis because we're not graphing in the complex plane. So we're good. All set. All 3 of them are the answer. So Yeah, all three of those are possible roots. If you were to put in this number and cube it and then subtract 8, you should get 0. In fact, I think we could probably do that. Now, your calculator might have a little bit of an issue with the square root of 3 in terms of cubing it out and getting the right decimal value. But here, let me check it. Let's take -1 plus I. So where do you find I? Do you remember? I in your calculator? Second and then the decimal. I times the square root of 3. So I and then square root of 3. Now let me do something kind of clever here. We're going to store that value in x. So the store key is down here. Store in the variable x right here. So press that one. And now to check it, what I want to do is I want to take x cubed and then subtract 8. So let's take x, it has that value in it, cube it, and then subtract 8. Now, I should get a 0. Now, occasionally you might get a little bit of a rounding error, so you might get something that's not quite 0. But cool, we nailed it. We got 0. So, there you go. You can check your answers on your exam. Pretty nice. Store button puts that value in the memory, so that you can recall it later. So if I didn't store anything else at the end of this afternoon, I could hit type the x where I stored this, and it's still going to have that value. So that I can use it later. Maybe I want to take and divide that by 2, so I can do whatever I want just using that value of x. No, it's not going to affect anything else. And if you're getting really nervous, what you could do is you can take 0 and store it into x. That way it kind of clears it out. But no, it won't affect anything else. Now there's a nice theorem that we should discuss. And it seems like some of your upper level classes, like this one in calculus, have what's called a fundamental theorem. And algebra is no exception. So let's discuss the fundamental theorem of algebra. All right, so here's the fundamental theorem of algebra. It says that each of these polynomials with complex coefficients or real coefficients, because real coefficients are kind of a special case, has at least one complex 0. At least one number that's going to make that equal to 0. Now we can go a little bit further than that. And let's go to the Zeros Theorem, which I think of more of as being really the fundamental theorem. And basically what this is saying is if you have a degree n polynomial, you're going to have n roots. Now some of them may be repeated, but you're going to have n roots. And let's look back at our previous two examples here, problems number 8 and 16. In problem number 8, we had a degree 5 polynomial. We found two roots, right? X equals 0, actually 3 roots, plus 3i and negative 3i. But if you count for the multiplicities, 3, 1, and 1, then you've accounted for all 5 roots. The number of roots should match the degree. You should have a nice correspondence. If it's a degree 5 polynomial, then you're going to find exactly 5 roots, as long as you count the multiplicities. This is a degree 3 polynomial. We found 3 roots. We know we can stop, because once you found 3 roots, you're not going to find any more. That's it. So there's a nice correspondence between that and your degree. Now, the guy who proved this is worth just a moment of mention. His name is Carl Friedrich Gauss, and he was a prodigy from early on. As a 3-year-old, looking over his dad's shoulder, his dad got down to the bottom of a column of figures, adding them up, and little Gauss whispered in his dad's ear, "No, Dad, you got the wrong number." And he told him the correct number as a 3-year-old. His dad wasn't even aware that he was watching. As a 10-year-old, now Gauss was a German mathematician, and as a 10-year-old, he was in class with like 50 other kids, and his instructor got mad. He's like, "All right, that's it. I want you to add up the first 100 numbers." And he gave it to him as kind of like a punishment. Now for the instructor, it's not a big deal because there's tricks you can use. But for Gauss, all he had was a chalk slate. Because back in those days, you didn't have pen and paper. He had a chalk slate, and he sat there and he thought about it. And he wrote down exactly one number. And that one number, 5,050, was the right number. He's the only kid in the class that got it. And so this really hard case of a professor did history a favor by giving Gauss an advanced book in math, and then eventually hooking him up with a tutor who could go further with him than the instructor could. But Gauss was amazing. He did a lot of stuff. If you were to list the top 3 mathematicians of all time, you'd have Archimedes, who was a Greek mathematician, a couple hundred BC, Gauss, and one other name that you know, and it wasn't mine. And Einstein was a physicist, but he was certainly a pretty brilliant guy. What's the other guy? The Apple guy? Newton. So that's some pretty good company. Anytime you're on a list with Newton, that's really good company. All right, so let's go back to section 3.5 then. So there's this nice correspondence between roots and factors. There's also something else that we saw, but we really didn't take the time to observe in the first couple problems. We had a root at 3i, and we also had a root at negative 3i. These are called conjugates. Down here, we had a root at negative 1 plus I squared to 3, and negative 1 minus I squared to 3. So if you have a polynomial with real numbered coefficients, your roots here, your complex roots are always going to occur in pairs. If you get one, then you have the other. So it's called the conjugate root theorem. It's something that I hold you responsible for. So if polynomial has real coefficients and the complex number is a 0 of the polynomial, then its complex conjugate is also a 0. Now, they use this bar notation for complex conjugates. So let me explain what that represents. If a plus bi is a root, its conjugate is a minus bi. So if you call this z, they're going to call this z bar. I'm not going to make you responsible for this notation. If you're reading the book, well, at least you know and have seen this notation. But I'm not going to make you responsible for it. It's nice, it's handy, but it goes beyond what I'm worried about for you in this class. So where could we use that? How would we use it? Well, let's take a look at problem number 40. You're asked to kind of reverse engineer a polynomial with degree 3. So they tell you that n equals 3. And they have a root at 0 and a root at I. So that's the information that's given to you here. Now, if you're keeping track, we've only accounted for 2 out of the 3 roots. We need another one. There's another root that's missing here. Yeah, x equals negative I. This is implied by the conjugate root theorem. Because when you have this one, then you get this one. So effectively, this is 0 plus I. This would be 0 minus I. But I'm not going to write 0 plus I. I'm not going to write 0 minus I. I'm just going to write these two. All right, so you get this one from the conjugate root theorem. Let's take a look overall. Our roots and our factors. So we've got a root at x equals 0. Its factor is just x. If I have a root at I, its factor is x minus I. If I have a root at negative I, what's its factor? Good, x plus I. So if I want the polynomial p of x, I'm just going to multiply together all three of these factors. It's going to be x times x minus I times x plus I. My suggestion to you in multiplying these things together is to start by multiplying together the complex conjugate pairs. So these two. Now there's tricks, but it'd take me as long to do the multiplication as it would to explain the trick. So let's just FOIL this out. It's going to be x squared plus xi minus xi. So first outside, inside. How about the last term? What's the last term going to be? Good. Minus I squared. And that I squared is going to become negative 1. You'll have the negative of negative 1. So a lot of nice simplification coming our way. So an x still on the outside. Those two disappear. Those cancel each other out. This becomes x squared plus 1. And overall x cubed plus x. So that's your polynomial p of x. And it's kind of neat that you can reverse engineer that one. We started out with the roots, not even all the roots. Started out with the roots and then figured out the polynomial. How are we looking on problem number 40? We're okay there? Good on that one. Let's try a couple more here. Problem number 44. X equals 2i, x equals 3i, and n equals 4. Let me make that same list that we did just a minute ago. Roots, and then factors. We have a root at x equals 2i and x equals 3i. If you notice, I gave myself a generous amount of space between the 2i and the 3i. Any suggestion as to why? Why did I leave that space? Good. We get a couple bonus roots. From the complex conjugate root theorem, we get minus 2i and minus 3i as roots as well. So these come from our conjugate root theorem. What are the corresponding factors? X minus 2i, x plus 2i. Good. So these are all our factors. Let's create the polynomial by multiplying together all these factors. So what I would suggest is you kind of work at it pairwise. Let's start with these two here. So much for that pen. So let's start with these two here. Multiply those together. And then likewise, let's do these two here. Now you may get pretty good at multiplying these things together, and that's fine. I'll get x squared plus 2x plus 2xi minus 2xi minus 4i squared. I need to get some nice cancellation there in the middle. those will disappear. It'll leave me with x squared plus 4. See what you can come up with for the second pair. See if you can't finish that one off. You should have gotten x squared plus 9. And if I FOIL that out, I'll get x to the 4th plus 9x squared plus 4x squared plus 36. Overall, x to the 4th plus 13x squared plus 36. That is your p of x. If I were to look at this graph on Desmos or on my graphing calculator, can you make any predictions as to what I would see?
You can see it not hitting the zeros.
Yeah, it wouldn't hit the x-axis, right? So the end behavior here, because it's a polynomial of even degree, the end behavior would direct those two kind of tails of the graph up. It would have a y-intercept at 36 and no x-intercepts. So let's see. I'm just going to graph it between -3 and 3. And let's go up to maybe 200. Let's see what it looks like. Okay, so there's the graph. Nice and symmetric. Not a surprise there. But it doesn't touch the x-axis at all. And it shouldn't, because there's no real roots to this polynomial. Let's do one last one like this. The little trick in this, where it gets a little bit more difficult, is if you have something a little bit more involved for your complex root. And we'll see that with problem number 42. We want a degree 3 polynomial. So n equals 3. And we've got a root at x equals, was it -3 or 3? -3, thank you. So roots x equal -3, x equals 1 plus I. I also want the factors. Well, let's pause for a second. I've got a root at 1 plus I. Where's the other root? 1 minus I. Good, so x equal 1 minus I. Now the factors would be x plus 3 equals 0. And the second one's a little bit more complicated. But just carefully move these terms to the left-hand side. That's going to be x minus 1 minus I equals 0. And likewise, if I move this to the left-hand side, I'll get x minus 1 plus I equals 0. So there's your corresponding factors. But all you're doing is you're moving it to the other side. And when it changes sides, it changes signs. So 3 factors should give me my polynomial. It's going to be x plus 3 times x minus 1 minus I, x minus 1 plus I. Now in a problem like this, I'm a little bit torn. There's a couple ways to do this, but regardless of exactly how you do it, you should start with this part, multiplying these two together. So let's do that. And I'll show you both ways. I'll let you choose whichever one you like. The first way to do it is kind of brute force. I can't FOIL these. I'd run out of letters. I'd need 9 letters. So when you create a nice mnemonic with 9 letters, let me know. But good luck. You got first, and then beyond that, good luck.
Used to have one for the planets.
That's true. Well, they have one for like memorizing digits of pi. It's kind of like, oh, how are my headaches after lectures involving quantum physics? I need an alcoholic drink or something like that. But it's the number of letters in each word corresponds to the digits that you're supposed to use. Well, people have memorized pi out to over, I mean, the world record. Anyone want to guess before I spill the beans?
Oh, it's thousands, tens of thousands.
70,000 is the latest. 70,000 digits of pi. Yeah, get a life. That's a lot. That's an awful lot. All right. X squared minus x plus xi, and then distribute the minus 1. So I get a minus x, a plus 1, a minus I, and now distribute the minus I get minus xi, and then a minus and a minus is a plus I, and then the last terms give me a minus I squared. So, wow. Yeah, let me zoom in a little bit, right? So all I did is I distributed. Now, I was a little bit thoughtful as I distributed the last terms. In what way was I being thoughtful? Yeah, I put the like terms together so that they can cancel. This and this, the i's cancel out. Here and here, those cancel out. So we're getting some nice simplification. Let's see what's left. I've got x plus 3. And then inside here, I've got x squared. That and that are like terms. So there'd be a minus 2x plus 1. What happens to my minus I squared term? Yeah, so plus 1 again is plus 2. Last but not least, we've got to distribute this, or we've got to multiply this together. This is going to seem like small potatoes compared to what we just went through, though. Before I move on to this, are we okay what we did with this one? All right. Let's distribute the x. It's going to be x cubed minus 2x squared plus 2x. Distribute the 3. 3x squared minus 6x plus 6. And then I'll get x cubed plus x squared plus 4x plus 6. Which part? Minus 4. Oh, minus 4x. Yeah. Thank you. Minus 4x. I was looking at that going, something doesn't look right about the signs. So thanks. Appreciate you catching that. So there's your polynomial. P of x. You can check that to a small extent. Any ideas how we can check that? We can check it with the roots. I was thinking of a little more technology here. What if I was to graph it? What should I see when I graph it? Yeah, you should see 1, 0, right? At x equal, what was it? Negative 3. So minus 4x plus 6. Beautiful. And that's exactly what we see. We see one root at negative 3. So it's a nice double check of your work here. Now, you're not going to have decimals when you're working your tests, but what will you have? You have your graphing calculator, all right? So you can plug that into your graphing calculator and see, all right, yeah, it has exactly one root at -3. So again, I'm encouraging you to check your work. Okay, I think we've nailed that. I think I've done enough with the complex conjugate roots there that I want to move on to a couple more problems, 48 and 56. So problem 48, P of x is x cubed minus 7x squared plus 17x minus 15. And let me get back to the screen. Sorry about that. There we go. Okay. So what do the instructions say? It says find all the zeros of the polynomial. Wow, it's a big task. Where should we start? They ask you to find all the zeros.
Y equals
Y equals 2?
a 0 would be 2. Oh, sorry, that's wrong. Use your theorem.
Which theorem? Rational root theorem? Sure. Let's start out with the rational root theorem. P would be the numbers that are divisible into 15. So 1, 3, 5, and 15. What's Q? Just 1, right? So that's pretty helpful. If we're going to have a rational root, of course there's no guarantee that we will, but plus or minus Q is going to be plus or minus 1, 3, 5, or 15. Now that actually kind of gives you an easy way to set up your window. If you didn't know what to do, you could set it up so that you could capture the biggest or smallest that your rational roots could be. So you'd go from, say, -16 to 16. Now I'm going to help you out a little bit on this one. I would suggest that we set our window according to this. -4 to 8 by -30 to 30. Half of me thinks that I should probably just let you fuss with it yourself, but I don't like to spend too much time in class on that. It is something that I would encourage you to spend some time on at home, figuring out some good windows for these graphs. Maybe we'll do that on the next one. So make sure you change your function. Enter the new function. If you have the old function, it's not going to help out too much. So x cubed minus 7x squared plus 17x minus 15. Where does it look like our graph's hitting the x-axis? 3. You can check that with the trace key, but x equals 3. Nice. So let's take care of x equals 3 as a root, and then worry about what's left over. So at x equals 3 as a root, let's divide by synthetic division. 1, -7, 17, -15. Put our 0 here. Kenny, sorry, I'm stole your thunder. 3 there, -4, -12, 5, and 15, and 0. So what's that tell me about P of x? P of x can be written as x minus 3 times what? times what else? Yeah, thank you. X squared minus 4x plus 5. Lucas, I'm tempted to ask you how that factors, but it doesn't. All right. So I need to continue finding where this equals 0. I know where this equals 0. X minus 3 equals 0 when x equals 3. We already knew that one. But where does x squared minus 4x plus 5 equal 0? What am I going to have to do there? Quadratic formula. So x equals negative of negative 4 plus or minus a square root of negative 4 squared minus 4 times 1 times 5 over 2 times 1. So it's 4 plus or minus the square root of 16 minus 20 is negative 4. Square root of negative 4 is 2i. Let's be careful. This needs to divide both of these. Or you could factor out a 2. I like that better. Let's factor out the 2. That 2 and that 2 cancel. I'm left with 2 plus or minus I. If you look at the graph on this one, in fact, we looked at the graph and we saw it cross the x-axis at exactly one place, at x equals 3. Your other two roots are imaginary. And notice again they occur in complex conjugate pairs. But the idea is to get at least one of those roots. And then use synthetic division to kind of work your problem down into something more manageable. X equals, or x equal 3. So those are our roots. How are we looking on 48? Are you ready for one? All right. Yours is going to be a little bit bigger. It's going to be a 4th degree polynomial, but it's going to be the same workflow. Start with the rational root theorem. Figure out the rational roots, graph it, choose whichever rational roots appear obvious. Use synthetic division to pare down your polynomial to help factor it more. And then with whatever's left, if you can get it down to a quadratic equation, then great. You can always use a quadratic formula. So let's take a look at problem number 56. So P of x is x to the 4th. I've got a minus 2x cubed. Is that right? Thank you. So minus 2x cubed minus 2x squared minus 2x minus 3. Now, I think I promised on this one that we would spend a little time playing with the windows. So let's do that. Let's put in our function. Oops. Clear that out. So x to the 4th minus 2x to the 3rd minus 2x squared minus 2x minus 3. And if I just hit the graph key using the window settings that I had from the previous one, let's see what I get. Not too bad, but there seems like some important behavior that I'm missing, right? The important behavior looks like that graph comes back and crosses the x-axis. So I'm going to do two things. I want to draw this farther to the right. What parameter do I have to change to draw it farther to the right? All right, I've changed something in the x-axis. You got to change x max. Good. So we're going to make x max a little bit bigger. And also, take a look at this space down here. It feels like it's kind of wasted, right? There's no graph here. So I'm going to make y minimum a little bit bigger. I'm going to bring that up so that I don't have all this wasted space down here. So we'll make two changes. And these are just guesses. You can always go back and change it some more. So I'm going to take x max out to, say, 5. Y minimum, I'm going to bring up to negative 20. I'm going to leave y maximum where it was to start with. So now let's take a look at our graph. And that looks a lot better. Notice that the graph is filling up the screen. So I'm happy about that. I mean, we could nitpick at this for a long time, but let's not do that. I'm not sure we really need the rational root theorem in this one. Do we? Can you kind of see where it's crossing the x-axis? So if you need to practice the rational root theorem, great. It's only going to give you a couple possibilities. But I think we can see them. If you trace it at negative 1, you've got a root. Trace it at 3, again, you've got a root. So use those two roots to kind of pare down your polynomial so that all you'd be left with is those two roots factored times a quadratic polynomial. And you should be able to use the quadratic formula to finish it off. So I'm going to walk around, help out. So for those of you watching at home, we got a little TV timeout here. But I'm giving you a chance to do this one on your own. And I'm going to try and put this here so that you can just fast forward these videos through this little dead zone. Help each other out. Amy and I are going to walk around as well. Yeah, start with the known roots. Like 1 and 3 and 1 and negative 1. So either one. Yes, you do. Because you can't use a quadratic formula for a full three polynomial. You got to use synthetic division a couple times to kind of work it down to reasonable level. So yes, I'm assuming it looks good. I mean, 3 is a root. You can see it from the graph, so you should have gotten 0 there. So far that looks good. Yeah. So, but you want to use it with reduced polynomial. So this is x to the third plus x squared plus x plus 1. So do it with the reduced polynomial. So we're trying to figure out where this b equals 0. So we know where it equals 0. Minus 4 is yeah. So 2x was set plus x squared plus 1 equals 0.
Shouldn't matter if it's negative because if it was, well, negative or the opposite, I guess it's different. But
Okay. So we need to figure out where this term equals 0. Because we already know where this equals 0.
because if it's square or negative,
So
you
just
get
set that
positive
equals 0.
anyway.
Right. That's all. Okay. Okay. We're trying to find all the values where it crosses the x-axis, or all the roots. easier than what you had. Okay, so I know of two roots. I know of roots at -1 and at 3. You can get that from the rational root theorem. It's just as easy, if not easier, to get it from the graph. So let's start out with root at -1. So 1, -2, -2, -2, -3. And the idea here is by getting rid of these, you're paring down the polynomial. You're giving yourself what's called a reduced polynomial. So 0 gives me a 1, -1, so -3, +3, 1, -1, -3, +3, 0. Great. So what effectively I've gotten here is that I can rewrite p of x as, well, what factor corresponds to this root? X plus 1 times x cubed minus 3x squared plus x minus 3. So nice. But we're going to continue working with this and the reduced polynomial. The other root that I knew of was at x equals 3. So 1, -3, 1, -3. Add, we get 1. Multiply, we get 3. Add, we get 0. Multiply, you still get 0. Add, you get 1. Multiply, you get 3. So great. What this is telling me now is that I can rewrite this as x plus 1, x minus 3. And what's this part right here? Good. X squared plus 1. Now keep in mind what Gauss taught us. If that's degree 4, how many roots should I be able to find? 4. I've only found 2. I want to know where this equals 0. I know where this equals 0, -1 and 3. So the remaining part is to figure out where x squared plus 1 equals 0. Now I don't think I want to pull out the quadratic formula for this one. Let's just move the 1 to the other side. Plus or minus the square root of -1 is plus or minus I. So all together we get roots at -1, 3, I, and -I. And there's your complex conjugates, degree 4 polynomial, 4 roots. I suppose if I wanted to, I could ask you to factor this. It's, I don't know, not that appealing to me of a problem, but you should be able to factor it. And there would be the complete factorization. So here's the roots right here. Here's the corresponding factors. All right, that's a wrap for section 3.5. For homework, try 7 through 15, 19, 21. Let me give you a hint that q of x can be written as x plus 1 squared plus 1. 23 through 29 and 37 through 55. That's section 3.5.